Assalamualaikum, I'm Arif Haikal. So let's start with the background. So, what is the problem and motivation? So, the problem is that the stock market data is non-linear, noisy, and chaotic, which makes prediction difficult. There are existing gaps, which are traditional models struggle to capture long-term data dependencies. So LSTM networks are powerful, but they rely on manual hyperparameter tuning. So there are baseline flaws, which is naive Bayes is unsuitable for time series. So it assumes feature independence and ignores sequential momentum. And for decision tree, it suffers from extrapolation failure. So it cannot predict trends beyond value seen during training. So our proposed solution is PSO LSTM. So so the objective is we implement a hybrid model integrating particle swarm optimization with LSTM networks. So it utilizes PSO to automate the search for optimal hyperparameters like hidden layers and learning rates. So the goal is to eliminate manual configuration to improve predictive accuracy and convergence speed. So the dataset we use is Bursa Malaysia KLCI index from 2010 to present to model local economic trends.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Mahyudin. Now I will proceed to the data analysis. Okay, so first let's talk about the data. When we downloaded the historical data, it's a bit messy and the computer couldn't read this properly. So we did four simple cleaning steps. Okay, for the firstly, we fixing the dates. First, the dates were actually the words when the raw data we extract, which is from the newest to the oldest. But since we are predicting the future, we need the data to flow forward. So we flip the list so it starts from the oldest date to the newest date. Next, we fix the price, open, high, and low column. Okay, so the price had commas in them like 1600. So the computer thought this was a text, not a number. So we simply remove the commas so we could do a math with them. And next, we fix the volume column. We look at the value column. It used like letter M for million and K for thousand. So we wrote a small function here to swap those letters for a real zero, turning them to something like 1 million to 1,000,000,000. And lastly, we fix the percentage in the dataset. We just remove the percentage symbol from the change column and now the data is all clean. So you can see here, the data is successfully cleaned by us. Okay, next. Okay, now that the data is clean, so we need to format it specifically to our model, which is LSTM model. So we firstly make a normalization. Okay, so the stock price can be a large number, which make the AI learn very slow. So to fix this, we use a mixed max scaler, which is this squash all the price down to a number between 0 and 1, and it make the training much faster and more stable. Next, we apply the sliding window, which is this is the most important part, which is we don't just show the AI 1 day at time, but we created a sliding window of 20 days. Think of it like this. We tell the model look at what happened in last 20 days and try to guess what happened on day 21. So it learns the pattern from these 20 days that we already do. And next, we splitting. We split the training and testing. So we need to test it if our model actually works. So we split our data set, which is 70 for training and 30 for testing. And lastly, we reshape the data into a 3D format, which is this is just a technical requirement because it's only shape the LSTM model accept as input. So we can hear that this is the result of our pre-processing and ADA process. Just that from me, I will pass to the next presenter. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Now we move to our next phase, which is our methodology. Okay, so to test our project, we compare four different models. We started with the simple one and moved to our advanced solution. Okay, first, we built a naive bias model, which is our probabilistic baseline. Yes, so the goals of the models is to predict the market direction, either it will go up or go down, rather than the exact place. And we use the technique of Gaussian probability to classify trend. Okay, what this mean? This mean that it doesn't try to guess the exact price. Instead, it just look at the probability to guess the trend. Basically, is the market going up or down today? You can hear the graph show at the up or down. Okay, next, we try the decision tree model. So, this model is a classical machine learning model. It's not a deep learning baseline. So our goal is to predict a specific price using a traditional price feature. So we set up it by using the fixed random stick to ensure the consistent result. What do you mean by that? We use this to see how well a traditional method could predict the actual price compared to our more complex AI. Then we build a standard LSTM neural network. Okay, so this is our first deep learning baseline. We set it up with the standard structure, which is two layer with 120 neurons, just to see how a normal AI perform without any special tuning. So we train it using 64 epoch using the Adam optimizer. Okay, for the lastly, finally, this is our core of our study, which is the chosen solution that we choose for our project. So, which is the PSO optimized LSTM. So, instead of guessing the best setting ourselves, we use the algorithm called particle swarm optimization, which is it act like a smart search engine to testing different combination of parameter tuning until it found the perfect architecture, which is turned out to be a deeper model trained a longer epoch. So as the result, the algorithm improved the structure to 68 and 147 neurons with 92 equal a better accuracy. You can see here, this is the graph that we got by comparing the LSTM with the PSO. You can see here that the accuracy is more accurate than a standard LSTM. So just that for me, for the methodology, I will pass to the next presenter.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adam Mohaimin Bishanwali and with metric number 2319055. Uh, Today I'm going to continue the methodology for deployment process. First, we export the .h5 file which contains the actual BSO optimized model. Secondly, and this is crucial, we save the scalar object with file name scalar.pkl Since our model was trained on data normalized between 0 and 1, it does not understand raw currency prices. If we did not save this exact scalar to transform data, our prediction could be completely wrong. Alright, so for the step 2, we build the logic layer, which is the Python script called app.py. It tests an input of the 20 days of closing prices, which match the loopback window we use during training. Also, it automatically normalizes those values using that safe scalar reshapes them for the LSTM and runs the prediction. Also, finally, it does an inverse transformation to convert that 0 to 1 value back into a real ringgit Malaysia prices so the user can actually read it. For the final step is we wanted a user-friendly interface without writing complex HTML or CSS, so we used a library called Gradio. It gave us a simple dashboard for users to paste stock prices and predict button. We developed the whole thing on Hugging Face spaces. It is a great platform because it supports TensorFlow natively and gives us a permanent URL so we can easily share the project with EZ miners or future resources. Alright, so this is how the actual deploy tool looks like. As you can see on the left, there is an input box where the users simply paste the closing prices for the past 30 days. They don't need to worry about normalizing the data or coding anything because they just need to enter the raw numbers. When they hit submit, then when they hit submit here, our backend script takes over. It scales the data, feeds it into our PSO optimized LSTM model, and then converts the result back into the currency. As you can see here, the output on the right shows the final prediction, which is 1,635 ringgit 80 cents. So that's all for me.
So now I'm going to explain our code. So first, of course, we imported pandas, numpy, and matplotlib that we are going to use for the code. So then we loaded the dataset, the FTSE, KLCI, historical index price, and we fixed the date column. Why? Because LSTM needs the date to be from oldest to newest to learn the sequence of time. So we make it from oldest to newest. And because this is CSV file, it's the values are separated by comma. So we need to remove the commas and convert it to float. So this is what we are doing here. So for the volume, it uses M for millions and K for thousands, right? So what we did is we replace M with 1 million like this, numerical value, and we replace K with 1000 like this. So we apply the clean volume, and then we also need to change the percentage sign to numbers to float, because to train the data set, all the data need to be in numbers, in float. And we check if it's successful, and as you can see, we have cleaned the data set. Because the CSV file is very simple, it's not complicated, it's very straightforward, so we don't have to do a lot of exploratory data analysis. We just clean what needed to be cleaned. So now this is just, we want to see how the closing prices look like from 2016 to the end of 2025. This is how the price is, and we are going to try to predict whether or not the models that we are going to implement can predict the price successfully. So now we import min-max scalar. Why min-max scalar? Because LSTM uses tan and sigmoid function, and the activation function is usually between 0 and 1 and -1 to 1, which is why we have to use min-max scalar instead of standard scalar. So here we take the price, the column that we are going to predict, we convert it to numpy arrays, and then we reshape it. This is to reshape it to 2 dimensions. Why we have to do that? Because the scalar and the model letter require it to be 2 dimension. So we apply the min-max scalar to the data, and we scale the data. So now what are we doing here? So we create a lookback of 20. What is lookback 20? 20 is the days that we are going to look back the prices, 20 prices that we are going to look back to predict the next price, the 21st day price. Okay. So why we minus the length of the data set with the length of lookback? Because we don't want the code to be out of bounds, because the code is written forward, it's not written backward. Okay, so if we keep looking back 20, even though it's the last element, it will be out of bounds. So that's why we need to minus it. So if the data set is 100, then the length is just 80. So here is just taking the window of the consecutive values starting from position I and extending for lookback steps to use for the input for the training. So this is the target label that the model is supposed to predict. So if we use the 20 days before to predict, this is the 21st day. So as you can see, we set the lookback to 20. Why 20? Why not 10 or 20? Because the research paper did experiment 10, 15, 20, 30, 60. They found that 20 gives the most accurate and less errors. So here we just split the dataset 70% and 30%. That is standard for LSTM. Why we don't use like k-fold, right? Because if you use k-fold to split, it will randomize the data. But for our model, we need the data to be in chronological order. It needs to be from oldest to newest. So we don't want randomized data, so we just split it 70-30 like this. So here, LSTM needs 3D input: samples, time steps, and price. So this is the sample, this is the time step, and this is the price. So this is the fourth cell. So first we create an empty neural network container. So for the first layer, we use 100 neurons. Why 100? Because the research paper, it used 100 neurons for the standard LSTM before we apply PSO. This is the standard one. So return sequences true. Why is return sequences true? So LSTM, it can either output the full sequence of the hidden states, each time step, or the last hidden state only. So because we are stacking another LSTM after this, because we have another layer that we want to give the steps to, we need the full sequence. So that's why we make return sequences as true. So this just tells the number of features per time step, which is 1. That is the 1 is the stop price. So for the second layer, we use 20 neurons. Because the research paper also uses 20, return sequences false, because we are not passing the information anymore. For the last layer, we just predict, so we don't need to pass detailed time steps. So it predicts one value, which is the stop price. So then we just compile the model. We use Adam optimizer with a learning rate of 0.001, which we will continue to optimize. Why 0.001? Because the research paper also used 0.001. And for the loss, we use mean square error for Adam optimizer. So again, we use the standard 64 epochs batch size 64, and then we make predictions. So as we know, the model converts everything to numerical numbers, right? It uses everything in float. So when it predicts, it might give floating number like this, which we need to convert back to price like this one. So we use the scalar that we created in the previous step to do that. So this is the evaluation metrics that we use: RMSE, MAE, and R-square. Why don't we use like accuracy or precision recall? Because this is a regression model. This is not a classification model. So the best way to calculate accuracy is by calculating RMSE. The lower the RMSE, the better. So this is the graph of the predictions. The predictions against the actual price. As you can see, it lags a bit if compared to the original price, but it still follows quite close. So because of that, we want to see the validation and training loss to see if there is overfit. And as you can see, over time, it starts to converge and there is no spike in validation loss. So it means the model is not overfitting. So for this code, it is the fitness function for PSO. We are preparing the PSO before we actually train the LSTM with PSO. So as we know, PSO, it creates particles or temporary models that will run with random numbers or random hyperparameters, and they will keep optimizing themselves. they will compare their self best with the swarm best. They will keep doing that. So for our model, we only choose 3 particles to make it faster for the demo. And for the first layer, we say that for the nodes, just pick random value between 10 and 200 for the 3 particles. So they will have random values. And for the second layer, also like that. And for the epochs, take random epochs from 10 to 100. And learning rate also the same, from 0.001 and 0.01, just pick randomly. And they will keep, the 3 particles will keep optimizing themselves and find the best hyperparameters. So this is the fitness function for the PSO. This is the function that the PSO will repeatedly call with different parameter vectors. So they are just unpacking the parameters here and convert it to integer. And then we build another model for the LSTM PSO. So the model, the first layer, the second layer, the third layer will use the hyperparameters found by the PSO. And as you can see, the other parts are just the same with standard LSTM. The return sequences through here because we want to pass the full sequences, all the time steps. Everything is just the same. And for epochs, we use the epochs that the PSO found also. And everything else is similar to standard LSTM. So now we start the actual PSO optimization. So W is the momentum or the inertia weight. So if the momentum is too high for the particles will just fly past the best values. And if it's too slow, then it will not change direction to keep exploring. So 0.6 is the balance, the best value. So this is the weights for the self best and also the swarm best. So we set the values to be the same. It means that both self best and swarm best are important. So we initialize the swarm, the velocities, which is the direction and speed of the particles, the best position each particle has ever visited, and also the fitness score of each particle personal best. So for the range of the number of particles, the number of particles that we use is 3 and 3 iterations. Why we use 3 particles? Usually people do 100, but for this demo we use 3. So as long as I is less than 3, we generate random parameters for the particles that they will continue to optimize. So this is the optimization loop. So as we know, we have 3 particles and 3 iterations. The 3 particles will continue to find the best optimization and pass the global best to the next iteration. So for this, if the score of the current particle is less than the personal best score that it found before, why less than? Because we use RMSE. The less RMSE, the better. So if it's better, then the current score, we set it to the personal best. And the best position, we set it to the current position. So this is the global best. If the score is less than the global best found so far, then the global best is set to the score and the position is set to the current position. So this is where we update the velocity and position of the PSO. So they use mathematical formula for it, but basically this is the formula to encourages momentum and exploration. This is the formula to find the best personal score, and it will make the particle move toward its best score. And this is the global best score, and the particle will move towards its own best score and also the swarm best score. So it stores the velocity in this. So this is the formula for updating the position, the velocity plus with the old position. So what are these? They are just to keep the particles to keep moving inside the bounds that we have set, because they might try to try random exploration or go outside of the bound. We need to keep them inside the bounds that we have set earlier. So now with everything that we have set, we run the PSO and see the RMSE. So before we run the PSO, right, to find the best hyperparameters, so it found 61 nodes for the first layer, 135 nodes for the second layer, 90 epochs, and learning rate of 0.0058 to be the best. So we just use that again and run the LSTM like usual with the best hyperparameters found by the PSO. So all the codes for the LSTM is just the same thing, and we retrain the model again with the optimized hyperparameters. So that's it for the code. Thank you. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Bashar bin Kamarul Anwar. Now I will be presenting our results. So let's begin with looking at the comparison table of all the models. This is the comparison of the quantitative performance for the regression models. Here we have decision tree, standard LSTM, and PSO optimized LSTM. Why is there no naive bias? Because naive bias is a classification model. These models are regression models. Naive bias can be used to predict market direction, while these models are used to predict exact closing price. That being said, we did train naive bias, but we will discuss the results later. So looking at the data, we can see that the decision tree has the highest error with RMSE of 16.71. That's actually quite high. This means that a simple regression tree struggles to capture the complex time series dependencies of the stock market. And the standard LSTM improved on decision tree with RMSE of 13.01. But as it is obvious, the best model is PSO optimized LSTM with RMSE of only 10.1. Okay, so it achieved the lowest RMSE and 22% reduction from the standard LSTM, reduction in error, and 40% reduction from the decision tree. This proves the effectiveness of using hybrid approach. So now let's look at this figure. This figure is the visualization of the actual price trend. The blue one is the actual price trend, the green one is the standard LSTM, and the red one is the PSO optimized LSTM. So if you watch closely, you can see that the green line, the green dotted line, it lags behind a little bit. As we can see here, the blue line, it moves down already, but the green line takes time to move downward. But as you can see, the red line, it moves almost the same with the blue line. Okay, and you can see this more closely during volatile period like this one. You see the blue line, it moves up, and the red line, it follows the blue line very closely, but the green line, it lags behind a little bit. So this confirms that the deeper architecture used by PSO, which is 135 neurons for the second layer compared to only 20 neurons of the second layer for standard LSTM, allowed the model to learn much more detail of the market features. So as we have seen before, our PSO optimized LSTM model followed the actual price very closely. So our concern is, did our model overfit? Did it memorize the data? So to investigate that, we have to look at the training loss versus validation loss. So from the start, the training loss was very high, but as the time goes by, it starts to converge, especially during 40, 50, 60 epochs. It starts to stabilize, but the PSO algorithm extends the training to 90 epochs. This extension allowed the model to extract maximum accuracy without the validation loss spiking. This proves that the model remains generalizable and stable despite the complexity. So we have seen the results of our regression models. We have seen decision trees, we have seen standard LSTM and PSO LSTM. Now let's see the naive bias model that we trained. So as you can see, the result is very disappointing. The model achieved accuracy of only 47%. That is lower than random guess. Random guess is 50%. The confusion metric shows even spreads of errors, but overall the underperformance highlights a crucial flaw of naive bias. Naive bias is not suitable to be used for this kind of time series type of data. So to illustrate even more why naive bias failed, we plotted these buy and sell signals predicted by the naive bias. The green one is buy signal and the red one is sell signal. As you can see, the model generates what we call as whipsaw signals. It keeps switching between buy and sells without capturing any sustained trends. Here, it tells you to sell, and then it tells you to buy, and then sell, and then buy again. So it is very inconsistent, and it is also giving buy signals when the market is clearly selling off. For example, here the market is clearly dropping, but it tells you to buy. So this confirms that for volatile financial data like this one, simple probabilistic models like naive Bayes cannot compete with deep learning approaches like LSTM or even decision tree. So finally, as obvious and evident, the winner out of all models is PSO LSTM. The superior performance of the PSO LSTM is because of two key factors. The first one is automated architecture search. As we know, traditional manual tuning relies on rules of thumb, like using 64 neurons or 128 neurons because they are power of 2. PSO explored the search space further and found a very non-standard configuration like 68 or 147 neurons that a human would never test manually, but the PSO found it as optimal. The second factor is the balanced complexity. The standard LSTM was likely underfitting or too simple because the second layer of the standard LSTM only contains 20 neurons, while the PSO algorithm identified much larger second layer, which is 135 neurons, to capture the non-linear volatility of the Bursa Malaysia KLCI index. So that's all for the results. I pass to the next presenter.
So, lastly, what is the conclusion and future work? So, the key results. We have seen that the PSO optimized LSTM achieved the lowest RMSE, which is 9.41. And for comparison, standard LSTM have 22% error reduction, and from decision tree it has a 40% error reduction. So PSO discovered a non-standard architecture. So it's like 68 and 147 neurons, which outperform manual architecture like 64 or 128 neurons. So for the conclusion and path forward, so we combined PSO with LSTM and it yields superior reliability over static classifiers. We deployed the model as a web app using Gradio and hosted on Hugging Face spaces for reproducibility. And in the future, we hope that periodic retraining can capture new market volatility, and we plan to expand, which incorporate additional technical indicators and test on other stock markets other than Malaysia's one. Thank you.